In this chapter, we're going to talk about diffuse lighting. First thing that I want to do is go over the theory behind calculating diffuse lighting and how it works, and I'm going to explain that visually using 3ds Max. And then the second thing that we're going to do is apply what we learned to the HLSL code, and I'll go in and make some additions to our base HLSL shader that implement the math that we've talked about. Okay, so what I've got here is a little sample scene. I've got a light source set up, and I've got a plane, and this cylinder represents the surface normal. The surface normal indicates the direction that the surface is facing. And what happens with diffuse lighting is that when the light source or the object move, the light updates to reflect the relationship between the light and the surface. So if the surface is pointing right at the light, you get a bright colored surface. But if the surface is pointing perpendicular to the light, you get a dark colored surface. So when we calculate diffuse lighting, that's what we're trying to achieve. We want to find out if the surface is pointing at the light or if it's pointing away from the light. So the way that we do that is, well, first of all, we start out with our surface normal, and then we have to create a vector between the position of the surface and the light source. So we're going to call this our light vector here. And the way that we calculate this light vector is by subtracting the light's position from the surface position. And when we subtract the one position from the other position, the result is a vector from one to the other. So now we've got our surface normal, and we've got our vector from the surface to the light. Now I should mention that in order to calculate this light vector here, we need to be sure that our surface position and our light position are both in the same space. They could be in object space, they could be in tangent space, they could be in world space, but we need to put both the light's position and the surface position in the same space as each other so that we can calculate that vector. And when I start demonstrating how this works in the code, I'll show you how to move them both into the same space. So now that we have our light vector, you'll notice that when the light's position moves, the light vector moves. So what we need to do to determine if our surface is pointing toward the light or away is measure this angle. This is the angle between the light vector and the surface normal. So if we measure this angle and we find out that the angle is really large, then we know that the surface needs to be darker. But if we measure it and we find out that the angle is really small, then we know that the surface needs to be bright. And the way that we measure this angle is with a dot product. And I'll show you in the code how you do a dot product. In order to do a dot product between two vectors, they both have to be the same length. And you'll notice that in this example, my light vector, the green one, and my normal are both exactly the same length. So we're able to do a dot product between the two. Now, generally when you first compute the light vector, it's going to be the distance from the surface all the way to the light. And so in order to do the dot product, the first thing that we have to do is normalize the light vector. And what normalization does is it makes the light vector a length of 1. So our surface normal is already a length of 1, and then we have to normalize our light vector to make it a length of 1, and then we can do a dot product. When we do our dot product, the result of the dot product calculation, if the angle is really shallow, right here, or really small, the result of our dot product is going to be 1. So if they're both pointing in exactly the same direction, our dot product will give us a 1. If the angle is a 90-degree angle, like this, our dot product will give us a 0. So then it's really easy to take that result and just multiply it by the color of the surface, and that's what gives us our diffuse lighting. So if our angle is 45 degrees, say, then the result will be 0.5, so we'll have a gray surface. And like I said, if it's pointing straight up, we'll have 1, so it'll be a bright surface. We just multiply 1 by the color of the surface, and that's what gives us our diffuse lighting. So anyway, that's a demonstration of kind of visually how diffuse lighting works. So now let's bring up Effects Composer, and we'll jump in, and I'll show you how to code what we've just talked about. So here's Effects Composer, and I've opened up the Chapter 12 Diffuse Lighting shader. This is where we're going to start. This is just a really bare bones shader, and all it does is return a color, just like the one that we used before. So the first thing that we need to do is bring in a couple of things that we don't have in here yet. The first thing that we need is the world transform matrix. So I'm just going to say float 4x4 world. We're going to use this to transform the position on the surface from object space to world space. So I'm just going to bind this to world, and I'm going to copy this little bit here so that we're not creating a UI element. So there we go. I'm bringing in the world transform matrix. The next thing that we need is the light position and the light color. And this is quite a bit to type, so I'm just going to copy it from another shader. And we're just going to put it right up here at the top. So this code that I've added here, we're creating a float 4 light position. And we're also bringing in the light color. All right, so let's scroll down here to our vertex shader and get to work. So far here in our vertex shader, the only thing that we're doing is putting the position into clip space and passing it out. So what we want to do here is measure the angle between the light vector and the surface normal. In order to get that angle, first we need to create a vector to the light source. And in order to do that, we first need to put the surface position in world space. So we're going to say float 3 world space position equals, then we're going to do some matrix math, in dot position, which is the vertices position in object space, and then we'll transform it with the world matrix. There you go. We'll leave a little comment here. Transform vert position to world space. Okay. The next thing that we're going to do is actually create our light vector. So we'll say float 3 light vector equals light 1 position. This value we're getting from here. So we're going to say light 1 position minus world space position. So we're subtracting the position on the surface from the position of the light. And that effectively gives us the light vector. The next thing that we need to do is normalize the light vector, because when you do a dot product to measure the angle between the two vectors, you have to have both vectors the same length, like I said. So the way that you do that is float 3, and we're going to call the normalized light vector L. So I'm going to say float 3L equals normalize light vector. So that makes the light vector's length 1. And so now we have the surface normal and the light vector both with a length of 1. Oh, one thing though, we haven't brought in the surface normal. So here's our structure that brings in the information that we need. And we need to add float for normal. So now we're bringing in the surface normal as well as the position of the vertex. And just to keep things clean, I'm going to say float 3n equals n dot normal. So now n is the surface normal that we just brought in. I'm just going to save it here to make sure I haven't made any typos. Yep, looks like I did. Yeah, I just misspelled position here. Okay, so moving right along, the next thing that we need to do is our dot product, and that measures the angle between the light vector and the normal. So what I'm going to do is say float brightness. Now remember that when we measure the angle with the dot product, it's going to give us 1 if both vectors are pointing the same direction, and it'll give us 0 if the angle between them is 90 degrees. So that's a float. So I'm going to call it the brightness because it's the brightness of the surface. And we're going to go dot n and L. So we're measuring the angle between the normal and the light vector. Now one thing that we didn't talk about when we did our little illustration here is that if the angle goes beyond 90 degrees, that's a problem. So in the code, we need to account for that. And what I'm going to do is make a new value. And I'm just going to call this, well, let's see, float, just call it brightness clamped. All right. And that's going to equal the maximum, whichever is greater, of brightness and 0. So this function here, this is a built-in HLSL function that returns the greater of the two numbers. And basically what it does is it sets the floor at 0. So my brightness value is not allowed to go any lower than 0. All right, so we're all ready to calculate our diffuse color now. I'm going to say out.diffuse equals brightness clamped times light 1 color. So I multiply the surface brightness by the color of the light, and that gives me my diffuse color. Now one thing that I don't have this diffuse member of my outgoing struct. I need to come back up here and say float for diffuse, and I'm going to bind that to color. All right, now let's save it. And it looks like I didn't make any typos that time, so we're all good. Now the last thing that we need to do is come down here to our pixel shader, and instead of saying float for color equals this hard-coded white color, I'm going to change this and say float for color equals in dot diffuse. Now we'll save it. And now we've got a shader that calculates diffuse lighting. Let's switch over here to max. Gonna hide our little palette there. And let's unhide our teapot. There's our teapot with the diffuse lighting shader applied. Now what we can do is, as we move the light source around, you'll notice that it's calculating our diffuse lighting. Very cool. So when the light source is over here, these back faces are pointing away from the light, so they're dark. But when we move the light, now the faces are bright because they're facing the light. And since we multiplied by our light color right here, we can even go in and change the color of the light to something like red, for example. And now we've got a red teapot. So our light source is red. So let's go over this one more time, just a really quick review. In our code, the first thing that we do is the light position and the vertex position both have to be in the same space. So we're transforming the incoming vert position from object space to world space. And our light position is already in world space. So now that both the vert position and the light position are in world space, we can subtract the vert position from the light position, which gives us our light vector. Then we normalize our light vector, and we do the dot product between the light vector and the normal to measure the angle between the two. And then we prevent the result of our dot product from being less than 0 by using this max built-in function. And then finally, we multiply the result of our dot product by the color of the light and send the results out to the pixel shader. And in the pixel shader, we just set the color of the pixel equal to the color that we calculated in the vertex shader. So there you go. That's how diffuse lighting is calculated, and you should be able to write a shader that does diffuse lighting now. Pretty cool. That's just about it for the DVD. In the next chapter, I'm going to just have a summary of everything that we've talked about so far, then we'll close it up.